given on a conformal. Equal to geodesic length, and we call this block length correspondence, which is just a semi-classical version of the standard ADS3C52 duality. So here is the plan that I hope to realize today, and I will start from a short review, as I promised you, of this block length correspondence in the sphere case. Then I will switch to the torus, and we'll discuss various semi-classical conformal blocks and how they are related to each other. The point is that they're not quite independent and related to each other by a chain of connections. And then I will switch, I will use the symmetry argument, and will explain that the existence of these different semi-classical blocks is not occasional, because they can be traced back to the existence of the truncated, not truncated, contracted Virasoro algebras, because conformal block is quite model independent. It's completely fixed by using symmetry algebra, and this is why various derived objects of conformal blocks, like semi-classical blocks, can be understood in terms of operations done with the symmetry algebra. Then I will consider the so-called classical block, which is just a particular semi-classical block, and will give its holographic interpretation in terms of geodesic networks stretched on the formal ADS in the case of one-point correlation function. Okay, and then traditionally I will summarize the results obtained and discuss future perspectives. So let's start. We are on a sphere, and suppose we have endpoint correlation function composed of and primary operators with conformal dimensions delta. They are inserted on a plane, so we identify plane and sphere. So they are inserted on a plane in different points labeled by z and z bars. Those z bars are I decided just to write down the holomorphic part of correlation function, and I'll explain it some later. And we know that correlation function can be decomposed into conformal blocks by using particular OBE channel, and the expansion coefficient are identified with the structure functions, which are given here by C, and also we use a particular range of summation given by conformal dimensions. So dividing the correlation function into holomorphic and anti-holomorphic parts, we observe that the model independent part of correlation function is given by the so-called conformal block, which depend on the coordinates of operating insertions, on external dimensions delta, and on conformal dimensions of the exchange channel, which are denoted by deltas tilde. Okay, and also the conformal block depends on the central chart. And we know that in a given OBE channel, the conformal block is conveniently depicted by, say, the fishbone diagram, where straight lines correspond to external legs, while wavy lines are just exchange channels. And three of these coordinates which parameterize the external legs can be fixed by using global conformal symmetry to prescribed values of coordinates on the plane, namely to 0, 1 and infinities. Okay, in what follows we will be distinguishing between different semi-classical limits of conformal blocks, and these limits depend on particular behavior of conformal dimensions. So there are two types of conformal dimensions which we call heavy and light, and heavy operators or heavy dimensions grow linearly with central charge, while in the case of light operator, conformal dimension remains fixed independently of a particular value of the central charge. So having this in mind, we distinguish between three types of conformal blocks, and the first type is just what people call global conformal block. This is the case when all operators are light. Another type of conformal block is, in some sense, opposite to global conformal block is the so-called classical conformal block. In this case, operators are heavy, and there is also a bulk of heavy light blocks which interpolate between these two extreme regimes. So now we switch to classical conformal block, and there is a lot of evidence in literature that in the semi-classical regime, when the central charge tends to infinity, the conformal block exponentiates as follows. It means precisely the original quantum block is given by exponential with the exponential factor called classical conformal block, while these epsilon and epsilon tilde are called classical dimensions. They are given by ratios of original conformal dimensions and the central charge. So classical conformal blocks could be quite complicated functions with many interesting properties. For example, in the 4-point case on a sphere, classical conformal block can be shown to satisfy the so-called Pendergast equation. But for our purposes, we can use this heavy light perturbation expansion drastically simplifies the analysis of classical conformal block. It was originally introduced by Fitzpatrick, Kaplan and Walters. Unfortunately, this name is somewhat misleading, because by the heavy light perturbation expansion, I mean that a part of heavy fields, let me remind you that all fields in the classical conformal block are heavy. So a part of heavy fields are heavier than other heavy fields. So there are no place for light fields. Okay, and in the case we'll consider below, we take two operators to be background heavy operators, and in that sense they form background for other heavy operators. So we can introduce background and perturbative operators, and this choice greatly simplifies the whole analysis. Heavy operators, we choose the last two operators with equal dimensions and denote their respective classical dimension as epsilon h. So in order to develop this perturbation theory, we introduce small parameters given by these ratios,